Hi everyone, welcome to our webinar today. This webinar is being presented by the Clean Energy States Alliance, also known as CESA, and our topic for today's webinar is enabling high penetrations of distributed solar through the optimization of subtransmission voltage regulation. Our host for today's webinar is Nate Hausman. Nate is a project director here at CESA, and we have an excellent guest speaker with us today from Pacific Northwest National Laboratories, PNNL. Before I pass it over to them, I'd like to go over a few quick housekeeping notes. All of our attendees for this webinar are in listen-only mode. That means you can hear us, hopefully, but we can't hear you. You have a couple of options for the audio portion of the webinar. You can call in using a telephone, or you can connect using your computer mic and speakers. If you'd like to minimize the webinar console so that you can view the presentation full screen, you can click on the little orange arrow that you see circled here, and that arrow will also work to expand the webinar console. A very important note, we ask that you please submit your questions and your comments by typing them into the question box on the webinar console and hitting send. We will be saving about 15 minutes at the end of the webinar for a Q&A with the audience, and we would like to make sure that we answer as many questions as we can, so do type your questions in when you think of them. Don't wait until the very end. A final note, this webinar is being recorded. We will send you an email with a webinar recording within about 24 to 48 hours, likely today or tomorrow, and that will include a link to the recording and a PDF of the slides. And all of these webinar materials will also be posted on CESA's website at cesa.org/webinars. And that URL is good to know because it's also where you can find information about our upcoming webinars. So with that, I'm going to pass it over to our host for today's webinar, Nate Hausman. As I said, Nate is a project director here at the Clean Energy States Alliance.
Great, thanks, Sam. Yeah, sure enough, I am Nate Hausman, just in case you're not familiar with us, the Clean Energy States Alliance, or CESA, it's a national nonprofit network of public agencies and organizations. We work together to advance clean energy. We're mostly made up of state agencies, and you can see our members on this slide. Today's webinar is being conducted as part of our multi-state initiative to develop solar in locations that provide benefit to the grid. It's a CESA project, and under this project, we're working with 5 states and the District of Columbia to identify locations for solar and other distributed energy resources that provide meaningful benefits to the grid. We're working, as I mentioned, we're working with 5 states and DC. In Connecticut, it's the Connecticut Green Bank. In DC, it's the Office of the People's Counsel. In New Hampshire, it's the Public Utilities Commission Sustainable Energy Division. In Rhode Island, it's the Office of Energy Resources. In Washington State, it's the Department of Commerce, the State Energy Office. And in Wisconsin, it's the Office of Energy Innovation. Our multi-state project is part of the Solar Energy Innovation Network, which is a collaborative research effort to explore new ways solar energy can improve the affordability, reliability, and resiliency of the nation's electric grid. NREL is operating the Solar Energy Innovation Network, and they're doing it with funding from the Department of Energy's Solar Energy Technologies Office. So today's webinar is on a tool developed by PNNL. The tool can help planners and grid operators integrate greater penetrations of distributed solar. And here to talk to us about the tool and some modeling that the tool has been used for is Nader Samaan. And I'll just introduce him and then turn it over to him. Dr. Samaan is a staff power systems research engineer and a team lead for the grid analytics team within the electricity infrastructure group at Pacific Northwest National Lab, or PNNL. He's performing research in the areas of renewables integration, transmission planning, production cost modeling, and cascading outage analysis at PNNL. He's been doing it since 2009. Prior to joining PNNL, Dr. Samaan worked in Enernex Corporation as a power systems engineer, and prior to that, he served as a visiting assistant professor at Kansas State University. Dr. Samaan is a registered professional engineer in the state of Ohio, a senior member of IEEE Power Engineering Society. He obtained his PhD from Texas A&M University in 2004 in the area of power system reliability analysis. Okay, well, with that intro, I'll pass it over to you, Nader. The floor is yours.
Oh, thank you, Nate and Sam. Thank you everyone for attending this webinar. Good morning or good afternoon based on where you are located. So today I'm going to present the research work we have been performing for the last 3 years. And the presentation title is Enabling High Penetration of Distributed PV through the Optimization of Subtransmission Voltage Regulation. I'd like to give credit to the project team. This was a project led by PNNL in collaboration with University of Texas Austin, North Carolina State University, GE Global Research, One Cycle Control, and Duke Energy. So I will try first to explain the problem that we are trying to solve in this project. For those of you, maybe I'll start explaining the power network first. So there are 3 main components in the power network. There is generation, and there is bulk transmission, where lead generation is transferred to the demand or load locations, as you can see here in the lower part of this graph. And typically, the power system is designed for one way of power flow direction, from power plants through transmission to loads. But in the last maybe decade, this story has been changing, and we are having more what we call active distribution network, more distributed generation, which put potential of power flowing both directions, flowing back from distribution to the transmission network. A lot of work has been done on the impact of distributed generation on the distribution network, but very little work has been done on the impact or aggregated impact of distributed generation on the transmission network. We have done some work to figure out the impact of distributed generation on transmission, and we found there are issues such as voltage regulation. You start to see a voltage problem on the subtransmission network with higher penetration of distributed generation, such as distributed PV. And the system is not really designed to handle this reverse power flow. Like, all the devices there are mainly to support reactive loads. So you put capacitor bank in a substation to support reactive power, which, for those of you who's not familiar with reactive power, it is this other component of power, like there are real power and reactive power. You pay for real power, but reactive power is important to provide voltage support. It's needed for induction motors, like in your air conditioner at house, you consume reactive power. So typically it's served, or reactive power provided locally by capacitor banks, but with higher penetration of distributed PV, you can start see the need for reactive power could be lower because of the reverse power flow, and as a result you start to see a voltage problem. So in this work we are offering, or we have proposed or developed 2 different solutions. One is a tool for real-time operation. We called it Coordinated Real-Time Subtransmission Volt-VAR Control Tool, or CReST-VCT. And the main idea about this tool, how we can take advantage of distributed generation, specifically the smart inverter and distributed PV, and treat them more or less like a virtual power plant that can support the transmission network by providing or absorbing reactive power, and coordinate their operation or their work with other legacy components like capacitor banks and transformers, and so that we are supporting the transmission network. Meanwhile, we are not violating any constraint on the distribution side. We couple that with another tool for long-term planning, like for a utility. If you have this kind of tool, how you can plan for long-term penetration of PV, or how you can enable your system to be able to absorb higher penetration of distributed PV. So this planning tool, we called it Optimal Future Subtransmission Volt-VAR Planning Tool. And the objective of this tool is to determine, okay, what kind of reactive power devices I need to put in my system, given that I can take advantage of the PV smart inverter capabilities. In my presentation today, I'll mainly cover the operation tool. And the outcomes of, if we have this operation and planning tool, like the ultimate goal is to enable higher penetration of PV or distributed PV up to 100% of the substation peak load, without violating standard voltage standards, which are NERC standard on the transmission level, or ANSI or IEEE standard on the distribution level. Another objective or outcome would be that the utility will take less time. If your system is ready, it will take less time to investigate or approve interconnection request from commercial or residential PV. So in the next couple of slides, I'm going to little bit dig further into the problem, explain what is the problem that we are trying to solve. So maybe 5 or 6 years ago, PNNL did a study or solar integration study for Duke Energy, and we were determining the impact of higher penetration of PV on generation, transmission, and distribution. In this slide, I'm covering the impact on the transmission network. So on the graph on the left side, this is one single snapshot of the system. Like this is, I think, like 11 a.m. in a full day, and we are examining how voltage will look like at different substations. So this is maybe each bracket here or each column represent about 25 substations, and the blue line is voltage with PV, the green is voltage without PV. So as we can see, with moderate penetration of PV in this scenario, the voltage going from green to blue is getting higher. The lines above and below here are the limits, acceptable limits. So we start to see there's some violation happening under this penetration of PV. And this problem will be different. This is just one single snapshot. Like if it is a spring day or a summer day, this picture will be changing. But overall, yeah, you'll start to see overvoltage problem, especially in a rural substations where the load is not that high. On the right side, you can see the relation between the PV output and the increase in the voltage. So we can say it's somewhat linear relationship. The more the PV output there, you will have a higher voltage or bumping on the voltage level. Another piece that we looked at is how the current legacy devices are behaving. So the yellow here is these are capacitor bank switching on or off. The yellow is with PV, and the purple or pink is without PV. And we have seen that there is no really coordination between these devices, even though we are having overvoltage problem in the case with the PV, but these devices and other substations are still switching. So because they are really doing local control, they are not coordinated to work together. Another way to look to this problem, we take one of those substations and look to the one full day of simulation, and again look for one case with PV and another case without PV. And let me explain what we see here in this graph. On the upper left side, so the orange here is the PV output, and negative means it's moving from distribution back to transmission. The black here is the load at this substation, so it's a positive number. And then if you take the net load, which will be seen by the transmission, will be the PV or load minus PV, which will still be a negative number. So here that means that, say, at 3 p.m. you will have minus 15 megawatt or 15 megawatt moving from distribution back to transmission. Now, if we look to voltage profile, without the PV on the system, we'll get this green nice voltage profile, the dotted green line here, versus the dotted brown line, which is the voltage profile of the PV. So we start to see the voltage is getting higher and start to see overvoltage problem happening. Like, say, if your limit is 1.08 per unit, you start to see a voltage violation happening on subtransmission level with higher penetration of PV. And this is what I call low load day. This could be like a spring or fall day where most of the people are not running their air conditioning, so the load really is lower. If you look for another day, like say a summer day where many people are running their air conditioning, so the load is a little bit higher, and the net load going back to the transmission is not as big. We see the voltage is higher, like the dotted brown is higher than the green, but it's not as bad as we observe in the spring or fall day. So this problem will be more dominant during light load condition. So now, as I explain the problem, I'm going to explain what the solution we have been developing in this project. So as I mentioned, we are developing both operational tools that can coordinate voltage or coordinate reactive power taking advantage of the smart inverters on the distributed PV to act more or less like a virtual power plant, and coupling that with a planning tool. In year one, we have developed this algorithm or this approach or this software as a standalone tool using IEEE test systems. In year two of the project, we took it further and we were able to apply it for a whole Duke Energy system. And that's what I'm going to explain later in this presentation. And in year three, which we are in now, we are doing a very limited field demonstration and some hardware in the loop simulation, real-time simulation. And I'll talk about that in details in the next few slides. So let me explain our approach or our tool that we are developing here. So here in the left upper side, this is a transmission network. And you can see the distribution network is represented as this black line, it's just one single line. We don't see all the nodes and details on transmission model for the distribution system. So our approach starts with the transmission network. If we can decompose the transmission network into sub-control area for volt-var control, and each area will be associated with many substations or virtual power plants. And the idea here, you can see on the right side, so each of those, say the purple or green, is a subgroup for volt-var control, and each of them is associated with a certain number of substations on the distribution side. So each of those substations where you have maybe hundreds or thousands of loads and PV and storage, it will talk to the subtransmission or transmission module here, telling them, okay, as a virtual power plant, here is how much available to support you. Here's how much reactive power you can get from the distributed PV. Here's how much demand response storage and so on. And that will feed to the optimization at the subtransmission level. Based on this information, we'll determine how much support we need from each of those substations to maintain certain nice voltage profile at each of those substations, and send back this control signal to each of those substations. This would be the first level of optimization at the subtransmission level. Now we captured the relation or the interdependency between different substations. So we no longer need to worry about that. Each substation will try to do its own optimization in parallel. So each virtual power plant will try to meet the transmission requirement and do its own optimization to figure out, okay, to achieve this signal from transmission, how I can dispatch the reactive power in each of those smart inverters and the distributed PV without also violating any constraint on the distribution network. And that will happen in parallel in all those substations, hundreds of substations in parallel. So in terms of computational needs, the burden to decouple the interdependency was already taken as subtransmission optimization. Now each substation can optimize its own volt-var resources in parallel. So that should happen in a reasonable time for real-time application. Another piece of our work is how to model distribution in the transmission. Like, as I mentioned, it could be just one single node. In reality, distribution is thousands of nodes. Another piece we've developed here is a model reduction approach. So if we have this 10,000 nodes in distribution, if I can model them into, say, 8 or 9 nodes, so I get a better resolution for the distribution network in the transmission model. That's another approach. You can get a better way for how distribution will be those optimization for the transmission, though it could be achieved without it. So let me explain a little bit. Sorry, moved one slide further. I'll dig a little bit about the optimization problems. As I mentioned, this is a co-optimization approach. We optimize the transmission network and send the signal to distribution, which in turn will do its own optimization and send signal back to the transmission network. So in the transmission level, this optimization is what we call optimal power flow. It's based on AC optimal power flow. It's not the economics, like typically people, when they hear the optimal power flows, they hear about economic dispatch, like how you dispatch different generation units. But here, no, our objective really is to optimize reactive power. We don't touch real power. Real power is established through market operation and economics considerations. So all of that will be honored in our optimization. We don't try to change that. But rather, our objective function will have really multiple objectives that we try to achieve simultaneously. So the most important one for us is demand or substation voltage. We would like to maintain substation voltage within target level. In addition, we could achieve other goals such as, minimize the losses on the transmission network, try to avoid too much switching of the capacitor bank on the substations. Like, these are mechanical switches. We don't want them to keep operating all the time, because that will reduce their life expectancy. We want to avoid as much as possible curtailment of distributed solar, if any needed, and the use of demand response. Like, this could be kind of last resort because expensive. That will be subject to the typical constraint in AC power flow analysis, such as transmission line thermal limits, whatever schedules for the power plants, the bigger power plants, and their voltage schedules will be honored. The load, what's forecasted for the demand at each substation in terms of reactive power, and what was provided by the substation in terms of substation capability. Here's how much distributed solar can provide in terms of upper and lower bound of reactive power. So all of that would be honored. And the decision variable or control variables or output variables will be, here's how much reactive power I need from each substation or virtual power plant in terms of distributed PV, either absorb or deliver. If I need to switch any of the capacitor bank on substations, and if I need to use demand response, real or reactive power, or if I need to do any curtailment of PV. So that's the optimization on the transmission level, and which will be little block here, the orange box here. So this will be sent as a signal to the transmission network, which will be another level of optimization. So typically here, I just mentioned, like in our work, you can get like a planning model. It could be a FIME model, one of the software used for distribution planning. And we got the signal from transmission. We take that, and now in this particular work, we are converting that into OpenDSS, which is another tool for distribution planning. And we find ways to disaggregate load and PV. For transmission, the load and PV will look as one single injection, but in real life, you get this PV, say, distributed into maybe 100 locations. So, and one challenge, you may not have enough observability, like you may not have enough, a meter everywhere to figure out what the output of each load or each PV. So by observing some historical data, we can find intelligent way to kind of pseudo observability, disaggregate this signal into different loads and PV. And the optimization here is based on what they call voltage sensitivity matrix, or VSM. And the objective of this optimization, it has two goals. One is to meet whatever requirement coming from transmission. Second, make sure you are not violating any constraint within the distribution network. So you don't want to help transmission and mess up distribution. We need to make sure both transmission and distribution is okay. And the decision variables we are using here is the reactive power coming from smart inverters, BV curtailment if any needed, demand response, and voltage regulators, capacitor banks that are in the distribution side. And at the end, you'll be able to figure out, okay, here's what we were able to achieve, send that back to transmission, and okay, now at T+1 to in the next optimization time step, we tell transmission, okay, here's what we were able to achieve, and here's what's available for your next time step of optimization. So I want to also here in the next slide to show or talk a little bit about smart inverter capability, which was also part of this work. So a smart inverter, 4-quadrant smart inverter, This is the relation between real power, this is the y-axis here, and reactive power, which is the x-axis here. So typically we can say this is the relation here, this equation explains the relation, which is just giving you this circle boundary. So during, say, even nighttime, like you are not producing any real power, you can still, as a smart inverter, you can take a little bit of real power from the grid, and you can either absorb, which is minus Q here, or deliver reactive power, which is a positive Q here. And maybe worst case scenario is when you are producing your maximum output PV here, you don't have enough capability to move back and forth to provide reactive power. So if you really want to provide reactive power, you need to curtail a little bit the real power, and now you can move back and forth and providing reactive power capability. And for smart inverter, it can be controlled at different modes. Like you can say, send a dispatch signal, here's how much Q I need from the PV, or you can dispatch it by power factors, like try to maintain a constant power factor, which power factor represents the relation or the ratio between real and reactive power, or you want to maintain certain voltage profile at the local or the terminal of this smart inverter. So in our work here, we are using a constant Q or the dispatchable Q. So we send a Q signal for, here is what we need from each smart inverter. That's the control mode we are using for the smart inverter here. And we did some experimental work in UT to show that, yes, smart inverters can do that. GE is also doing some simulation in 1 megawatt smart inverter to show they are able to achieve this kind of capability. If you have older inverters or older PV projects and maybe several years old, maybe the current inverters, we don't have this capability. And the reason, because no one is asking for it. So when they build the inverter, they don't maybe make this capability as wide or as enabling because no one is asking for it. But with the new IEEE standards, that will be kind of the norm, that each smart inverter will have this kind of capability. So, and then in this next slide, I'm just explaining how we did the implementation, like how we spent 1 year of our life trying to implement that. So very quickly, you start from building a distribution model in a tool like OpenDSS, and this distribution will be connected with a transmission model, which could be a model in a planning tool like PSSE. And the GAMS will be the optimization engine here. And the whole code is developed as a big Python code that through API control all these modules. So at the beginning, the distribution model will send the signal to the GAMS telling them, okay, here's what's available. The transmission model will be topology, and generation dispatch will be read to the optimization model. And the optimization at the transmission level will be run and send the signal back to distribution here number 4, telling them, okay, here's what I need from you. And we put everything back on the transmission network, make sure there's a visible or operating point, and this process keep going back and forth. So it's thousands of lines of code here, but it's working. So let me explain the next few slides. I'm going to explain how we, in year 2 of this project, were able to test this approach in a full Duke Energy system. So we are able to leverage some of the previous work we did for Duke Energy. So typically you say, okay, here's the future year, like say year 2025, and I want to see how my system will look like, and with 25% of distributed PV penetration, and what's the impact on the system. So start what we call resource planning. You figure out your cost of utility, and they decide, okay, here's what kind of power plant that will retire and what new addition will happen. And so you really get a good prediction of how my system will look like 10 years from now. And then the next step will be trying to mimic system operation using production cost modeling, which will simply dispatch your resources, your generation, to figure out how my generation will move to meet the demand, given that I have this amount of PV in my system. And you can run a case with and without PV to see the impact of higher PV penetration in your system. So using this, you will end up having like one snapshot of your system every hour. If you want to dig further, we have a tool at PNNL developed to, even during the minute-to-minute operation, how units on EGC, automatic generation control, will keep moving up and down to meet the system imbalance. So we can get like minute-to-minute snapshot of the system operation. We can import that in a planning tool like PSSE. So in this way, we are having kind of a pseudo snapshot of the system at higher resolution that we can use in our analysis. That kind of mimic a market or how things will work in real life. So when to develop such a model, we start with a full interconnection from the Eastern interconnection, and then we develop an island for the Duke Energy system, and we honor the interchange schedule between this balancing area and neighboring balancing authorities. And we did some validation, like we take historical data, put in the model, and compare simulation versus historical data to make sure the model really is representative of reality. In terms of PV, or let me talk here a little bit first before explaining how we develop the PV time series. So the Duke Energy system in the Carolinas, we have two balancing authorities, about 40 gigawatt of load. And in our simulation, we consider a case with about 25%, which about 9.5 gigawatt of solar. In our simulation, we consider one of those balancing authorities, the DEC, which has about 3,000 buses or substations, about 200 or power plants, or what we call generator buses, and about 2,700 load buses, and the load is about 20 gigawatt, and the PV penetration about 5 gigawatt. And the total generation installed in conventional generation about 25 gigawatt. And we work with Duke Energy and PV forecast developers to develop scenarios for the PV penetration here, which are here the blue dots here, and the dot size represents the project size. And you put some assumption about how much commercial, how much residential, and so on. And by the zip code, you select the previous weather year, say 2013, and say the weather will look like that in 2025. You synchronize your load and PV, and you end up with 1 minute resolution time series of PV injection at each of those substations, and similar for load and so on. So you really have how my system will look like if all of that happen and together. So another piece of the work here, I talk about decomposition. This is another piece of work, say, like in Duke Energy, you have like 3,000 buses. If we want to do volt-var control, and we can do it as one big optimization problem, or if we want to slice it into 10 optimization problem at the transmission level, we were able to do volt-var sensitivity analysis and say, yeah, we can slice the system into 10 sub areas, and each area is about 300 to 400 buses. So that could reduce the computational effort. And in this case, we are able to control each area, volt-var control, without really missing a lot, because we are assuming the interdependency between these 10 areas is not that big for volt-var optimization. From the distribution side, we took data for about 3 substations and a total of 10 feeders, and we got the model in SIME and converted that to OpenDSS, which we are using in our tool, and we do some benchmarking to make sure the models in OpenDSS are equivalent to the model in SIME. And here is just like the error range, which was very minimal. So that again gave us confidence in what we are modeling is correct in our case. Yeah, on this slide, I'm showing, like, again, on the distribution side, these are 5 feeders, and this is how we take the transmission assumption in PV and put it back on the distribution. So, for example, here in this feeder, we have like 3 utility scale with total capacity of 3,000 kilowatts, and then how many residential PV we have, and so on. So we figure out the mix and try to distribute that on the distribution model. And it would be a mix between what project already exists on the distribution versus future project to meet the target level of penetration. So in the next couple of slides, I'm going to share some of the results we had in running simulation on the Duke Energy system. So this is a winter day, again, modeling it at 5-minute resolution. We did compare between two scenarios. One scenario, okay, business as usual, let the PV operate at unity power factor, so the PV is not providing or absorbing any reactive power, versus another scenario where we are applying our tool, CReST-VCT. So here in the left side, the upper graph, this is voltage profile at the substation as seen from the transmission side. And the red is the voltage profile without any optimization. Simply let the PV operate at unity power factor, which is the current business as usual model, versus the blue, which is coming from our optimization, where we are here trying to target and try to maintain a very tight voltage control on the voltage profile of the substation. So overall, we can see the blue line, we're able to maintain the target voltage very well within the required boundaries. From the other side, in the lower side of the graph, this is the orange is the PV output, and the red one, this is the PV output, I mean real power output, and then the red one is the reactive power output as aggregated from distributed PV as seen from the transmission side. So you can see here what's happening, like during the early morning hours, the PV or aggregated response from distributed PV was positive reactive power, which means it was providing reactive power which will be translated into supporting the voltage up, and as a result, the voltage is moving from this red line to this blue line. And during the day, we have a higher voltage, so we want to take this voltage down, and the aggregated response from PV, as we are expecting, was absorbing reactive power, so that to bump the voltage within the required limits. So here, yeah, seems things were working as expected, and we are able to take advantage of smart inverter capability or aggregated response from the PV. And this is just one single snapshot from one substation. If we take on the right side, this is the distribution of voltage deviation from a target value. So the red is the business as usual. Again, the blue is with the optimization. So now we are having almost able to very little deviation from target value of the optimization, and we're able to get rid of this red part here through the optimization. And this is representing like simulation done at 5-minute interval for almost 3 months at 5-minute resolution. So that's a huge amount of data we are showing here. And this is capturing voltage at different demand buses on the network. So this is how things will look like on the transmission side. Let us take a look on how things will look like from the distribution side. So in the distribution, you have, for this particular substation, you may have several thousand of nodes. And on the left side, the lower graph on the left side, this is a voltage profile at different nodes in the distribution. And the red lines here are the limits. And you can see there could be violation of these limits in the business as usual model, like if you don't just let the PV operate at unity power factor, versus the graph on the upper left side where the distribution is able to achieve two goals. It makes sure that it's able to support transmission by their request, and meanwhile it makes sure that we are within the boundary of the distribution voltage limits. We are not violating any limits on the distribution side. And on the right side, the graph on the right side is showing the reactive support from the distributed PV. These are the boundary, the one here in purple. Here's how much positive or negative the PV can provide. And the green is the signal from transmission. The dotted line is the capacitor bank on the distribution side. So, and the red is the response or reactive power aggregated from all the distributed PV. So if you add the red line and plus the dotted black line, you're able to meet the green line, which is a requirement from transmission. And once the capacitor bank switch it off here, now the green and red line are perfectly matching. So the response from distributed PV was very good and able to meet transmission requirements as needed. So that the optimization on the distribution side was successfully were able to be performed. We called it here VLSM control algorithm or voltage load sensitivity matrix. I'm not going to dig into the math details behind that. Okay, now I'm going, the next couple of slides, I'm going to give you just what we are doing now. So in simulation, everything seems perfect. It's working fine. Now we need to look further into some practical aspects. What kind of communication delays we could have? Is that really applicable in real time? And can we do it every 5 minutes? Concept like fail-safe, we need to make sure that's the case. Will optimization happen in reasonable time and so on? So we're doing what we call real-time simulation, which means like if you want to simulate 2 days, it will take 2 days to simulate that. You can simulate communication protocols and see if your algorithm really is working, can be applicable in real life or not. So currently we are developing, or we develop a platform where through OpenRT, which is a platform for real-time simulation, where we are modeling distribution network or transmission network at PNNL, distribution network at North Carolina State University, and actual PV inverter models at University of Texas. And we have been doing simulations in real time, communicating between these different modules and see if what we have done in simulation can work in real time. Until now, it seems working fine. We are able to achieve things within less than 5 minutes. So in terms of applicability in real time, it's working. We're still investigating different options for communication protocols, which one is better and so on. Another piece of this work that we are trying to do in this year is a limited what we call field verification. We are trying to get like day ahead forecast for one of the substations from Duke Energy, what their forecast for load and solar for the next day, and figure out, okay, how we can dispatch a commercial solar plant, the active power from this solar plant to maintain certain voltage level. So here we are not really doing co-optimization between transmission and distribution, because that would be very difficult to do in just a few months, but we are at least trying to show the distribution part, how we can build on forecasted data, how we can dispatch this solar plant reactive power to maintain a nice voltage profile at the substation level. So in conclusion, this is my last slide. We were able to show that how a coordinated real-time subtransmission volt-var control tool can be implemented considering the distributed PV as more or less like a virtual power plant that can provide active power support to the transmission network. We're able to show how the PV inverter models for active and reactive power regulation can be modeled and taken into consideration, and we are able to validate the capabilities of smart inverters. And the result we have obtained till now is achievable by taking advantage of those smart inverters capabilities. And the idea, or what's unique about this approach, is the co-optimization between transmission and distribution. And in general, we believe that the implementation of such approach would enable higher penetration of PV on the system, and by taking advantage of smart inverters. And rather than considering the higher PV penetration would be a negative issue or have a negative impact, we can actually take it more like a positive aspect that can provide support to the transmission network. Yeah, and I would like to acknowledge the financial support of this work through the Solar Technology Office at the Department of Energy, and I'd like to thank the project managers there, helping us and continuing discussions about this work. And I'd like to thank you all for listening and for your time today. And just want to mention that we have, if you really would like to learn more about the technical aspect, we have about 17 papers, maybe 3 or 4 journal papers, and another 12 or 13 conference paper explaining different aspects of this work. So it's available on the ResearchGate website, and the link will be available through the slide. So, and for sure, feel free to contact me if you have any questions. So thank you.
Great, thanks, Nader. That was very, very informative. So we'll turn it over for some Q&A and begin taking questions. The first question that I have is, once you sort of test and prove out your hypothesis around this optimization, what are ways that grid operators will be able to take advantage of? How can they take advantage of your optimization tool?
So our plan is at one point we will make it open source, like for anyone who is interested to test it, we'll make it available. Ultimate goal is we would be working with a vendor like EMS, DMS kind of vendors who are willing to take this approach and integrate it into their system. It's kind of a chicken and egg problem because the utility needs to ask for such a system, so the vendor will be willing to obtain it. So we are trying to do some outreach and part of this presentation today to make sure the math at least is working and that's doable. And yeah, there's would be happy to collaborate with vendors or utilities who would be interested to test that further. Yeah.
Great, thanks. This next question relates back to slide 6 or 7. So I don't know if we can scroll back to those slides. But the question is, even with no PV, the graph still shows voltage violations. This snapshot shows the PV making this problem only slightly worse. What is the worst added on overvoltage? Oh, this is the second question. What is the worst added on and overvoltage caused by PV that you've seen? That is the biggest gap in between the blue and the green lines.
Yeah, in this particular slide, this was only one single shot, like this is just one single instant. So I would say it could be why without the PV you see some violation. It could be some adjustment needed in the model, like transformer setting and so on. But it was, in this particular slide, the level of penetration was not that high. Like it wasn't, say, 25%. It's maybe, I think, 5 or 7% penetration. But you still see, yeah, the voltage problems are happening. And
I think we're actually, I think the question was actually referring to the previous slide. Sorry about that. Yes, that's the one.
Yes. So that's yeah. So yeah, you can see in like here, yeah, that some of the green lines were in violation already. But in this particular instance, there were some settings that needs to be adjusted further. But in general, like we observe that the blue line is always higher than the green line. And because here we are only, I'd say the slide after where we are considering really a full day, that really gives you much better understanding what's going on. If you'd like to move to the next slide. It shows like a full day, like slide number 6, it shows a full day of simulation. So it will show the problem, how the problem is kind of getting worse. Like I think that was particular, here it was like 11 a.m., the other one, it will show you the whole day, and you can see the problem is getting worse, like in 1 p.m., where you start to see higher penetration of PV.
Can we move to the next slide, Sam?
Yes, so here, what is shown in slide 6 is a full day of simulation. What was shown in slide 5 is one single snapshot. I think it was at 11 a.m. And here the level of penetration is not the same. Like in the slide number 6, we have much higher level of solar penetration. So what I'm saying is that you can't really judge in one single snapshot, like to see what the magnitude of the problem. You can't judge that on one single day of simulation. You really need to at least do tens of days of simulation, and more preferred to do it like for one full year to really understand the limit or the dimension of the problem. Thank you.
Great, thanks. Nader, how would you recommend facilities manage their load power factor under the new smart inverter regime that applies to distributed energy resources on their facilities? Note power factor penalties are still in effect in most areas.
So I think the issue here it's kind of what the relation or what kind of arrangement needs to be done between the utility and the PV plant owner, especially like commercial and like few megawatts kind of projects. I think are they willing to let utilities get control of their smart inverters, and will they ask for a price for that? Or simply that would be part of the requirement for the interconnection. Like, yeah, if you give me control of your smart inverter, I'll do my best not to curtail your real power, but I'll control your active power to maintain certain voltage. I think the concept of maintaining one single power factor is, as you have higher penetration, will not really work because you start to see problems like unity power factor will not be sufficient. The other issue is the coordination between different projects. Like if you try also to let each project maintain its own voltage target, you may start to see different smart inverters are kind of fighting between each other. So there are several approaches. Like we are here presenting this optimization coordination between all these devices together. Some other approaches are using group control. Like, okay, if any changes, all of the smart inverters will change simultaneously, and so there are a couple of different approaches. But I think PV developers are more and more willing to let utilities controlling their smart inverter. Otherwise, they may get to the point where utilities simply saying, no, we can't do it. We can't allow your project to be connected without significant investment in our system. And as utility would be asking for this capability for smart inverter, I think the new project will also ask the manufacturer of the PV panel smart inverter to have this kind of capability. So I think, yeah, it will evolve with time, and business as usual will not keep continuing as we have as the penetration level is increasing.
Great, thanks. Can you discuss the planned communication systems for your field deployments, protocols, and methods?
So currently, as I mentioned, in our limited scale field demonstration, we are not able to do it in real time because currently Duke Energy has no communication with the smart inverter of this utility scale solar plant. That's why our approach is we take a day-ahead data, like here is the best forecast we have in terms of PV and load, and put in our planning case that represents the feeder distribution system model, and based on that, we come up with, say, 24 values of power factor or active power dispatch for the solar plant, send this to the solar plant owner who will change their active power each hour and correspond to our analysis. So ideally, you would like to do that in real time, but currently there is no, the DMS or the distribution management system, Duke Energy doesn't have communication with solar, utility scale solar connected to their system. So, but we are doing that through the OpenRT simulations and exploring several modes of operation, different communication protocols. So there is no one certain protocols that we are at this point recommending or saying this one is better than this one. We are still kind of investigating that further.
Next question is have you modeled what happens when you add battery storage on site such that the batteries are available for both P and Q? Does that simplify the situation for substations?
So the answer, we didn't include storage in our simulation. Like that was kind of part of our future work wish list. Yeah, storage has a smart inverter for sure connecting to the grid, so it will have similar capability in terms of providing reactive power. You can also control real power. As I mentioned, we are not controlling real power in this work. We are simply honoring any decision. So it's kind of real power and reactive power decoupled from each other. But I agree that having storage in as part of that would be more like ancillary service that storage is providing in addition to real power, which will maybe have more value for storage, could be part of this optimization. So reactive support could be coming not only from smart inverters from PV, but also from smart inverter that connect storage with the grid.
Great, thanks. Next question. At the time when reactive power is absorbed by the PV inverter to allow for full real power output while maintaining voltage limits, how are the real power losses of the transmission and distribution systems associated with the increased VAR flows accounted for?
So yeah, so I'm assuming the question is saying the PV is absorbing reactive power. Is that correct? So it's acting more like is that correct? Absorbing or delivering?
Absorbing.
Okay, absorbing. So yes, here the PV is acting as an inductive load, absorbing reactive power, and yes, that will increase the VAR flowing back from transmission to distribution. So it's kind of a trade-off. Yes, you'll increase losses, but in return, you are maintaining your voltage level within the required boundary. So I would say you can put part of your optimization as you are optimizing the distributed PV and how we provide or how we absorb reactive power. You can put another objective, minimize the losses on the system. But for sure, there is a trade-off. You can't. There is what you call a voltage violation, like you are violating the voltage limit. So that's why you are trying to absorb VAR. But there is no limitation on losses. Like there is no something like, okay, here is you are increasing the losses, so we are violating losses limit. There's no really limits on that. So it's always a trade-off between these two. But in general, I wouldn't expect that would be that much. It could be a few percentage, and it would be again part of what the consumer are paying for. Yeah.
Great, thanks. And we're almost at the hour mark, and we haven't gotten to all the questions, but I want to ask you just one more question here before closing out. This question says, if smart inverters are set by default at 0.95 power factor, does this already mitigate PV impacts and provide some benefits? In other words, without optimization.
So I'm assuming was 0.95 power factor leading or lagging, like absorbing or delivering reactive power. But I'm assuming there is no one size fits all. Like again, you can't just say for any system, if I set this reactive power to this certain value, I'm resolving all the problem. That will really depend on the topology of the system. Are you talking about rural feeders? Are you talking about urban one? How's the load and what's the level of penetration and so on? So I would say, yeah, it will be misleading to say one single value of power factor will resolve all the problems. And again, if it can work at low level of penetration, it may work for summer, but may not work in fall or spring. So it's really much more complicated than just considering one single value.
Great, thank you. So yeah, we've reached the hour mark, and I just want to thank you, Dr. Samaan. I really appreciate your presentation. Actually, before telling you about some upcoming webinars, is there any last words or thoughts you wanna leave us with, Nader?
Oh, yeah, I'd like to thank you, Nathan. I'd like to thank the audience for their time, and I'll be happy to answer any questions through email if any comes later.
Great, and there's contact information. Nader's email address is on this slide. Yes, so thanks again, Nader, and thanks to our audience. I do want to tell you about a couple of upcoming webinars. On April 4th, we're going to present a webinar titled Energy Storage in State Energy Efficiency Plans. It's lessons from Massachusetts. And then the following week, on April 9th, we're hosting a webinar on net metering, distributed solar valuation, and rate design. So we hope you can join us for these webinars. Thanks again, and back over to you for a closeout, Sam.
Thanks, Nate, and thank you, Nader. As Nate said, we encourage you to attend our upcoming webinars. If you'd like to learn more about CESA and our member organizations, you can visit our website, CESA.org. You can also find us on Facebook and Twitter. So we hope to see you at the next webinar. Thank you for attending this one today. Bye, everyone.